Okay, we're gonna now add um, to the picture of beams shear stresses. So we're gonna assume we're still assuming that the bending moments are a much larger concern than the shear stresses, but we're going to add whatever shear stresses there are back into the picture, which means that we're not going to be in the pure bending case. So the bending moment will be changing as you move from left to right, and so that lack of equilibrium in the bending moments is going to engender have to be balanced out by the development of shear stresses. And so that's how we're going to back out a picture of what the shear stress tau is, again, at some position y. So it will be a companion equation to the equation we developed for normal stresses minus my over I. So we're going to be doing shear stresses in beams. And in particular, this derivation is pretty strongly tied to it having a rectangular cross section. Okay, so this is going to depend quite a bit on the geometry being predictable and rectangular. And again, this is just equilibrium. So we want to relate now shear forces to shear stresses. Okay, so we skip. We're not going to talk about shear strains yet. We're just going to be jumping right to the shear stress picture using the information we derived for normal stresses. Okay, so there's a couple of pictures I need to draw to get us off the ground. So we've got, let's say, a beam, like so. It has a neutral axis. Okay. And let's, again, take a little length dx slice out of the beam. And we want to measure, let's say, up some distance y from there. All right, I think we'll use y1 because there'll be another y here that I'll use in a minute. If you look on either side of this cut, we're going to have a moment and a shear V. And on this side, we're going to have some change in the moment, right? It'll be m plus some differential change, m dm, and then we're going to have the shear stress V, which will assume to be equal on both sides. Okay, so we want to understand what the shear stress is kind of moving from left to right or right to left along the bottom of this little block. So you can see that we have kind of a block here above. It's a block above where we're measuring at y1, and there's going to be this little shear stress field will develop underneath this block, and that's what we want to examine. So let's go ahead and pull that out and look at it. So we have this, here's our little block again, and we have some normal stress field, right, acting on that guy, and a normal stress field acting on that guy. And we have the neutral axis, and then this was y1. Okay. And we'll call this sigma 1. This will be sigma 2. Now, they're not equal anymore necessarily, right? Because the moments, we're not in a pure bending case. So we're assuming that there's some change. And that change in equilibrium has to be offset by something we call shear forces. Okay, so sigma 1 is not necessarily equal to sigma 2. Okay, so sigma 1 in this case is going to be equal to minus my over y, where this is a different y. This isn't y1. This would be some other y up into this cross-section up here. Sigma 2 minus m plus dm y over I. Okay, so now let's convert all these stresses into resultant forces. So we have to multiply all of these stresses by some area in order to get a resultant force. So if we want F1 corresponding to sigma 1, it's going to be just the integration of sigma 1 over the cross-section, this cross-section right up here. Okay, and so that's m y over I. And I'm going to drop the minus sign for a minute because I'm going to talk about the sign convention for shear in just a moment. So let's just not complicate things by losing the minus sign. Okay. So F1 looks like that. F2 is going to be sigma 2 dA, which will be m plus dm y over I dA. Okay. And then there's a, like I remember I mentioned, there's like a distributed shear stress field that develops underneath there, and we'll call that F3. And so if you look at the same block now, but with the resultant forces, we have F1, F2, and then we're going to have this thing F3 that's going to be related to tau, right? Tau's up here. Okay, so now, again, let's just look at equilibrium. So if we look at equilibrium, we have F equals F3 is equal to, this is F1, F2 minus F1. Okay. So if we plug the expressions for F2 and F1 in, and we're going to end up being able to cancel out this m's, leaving us just with a dm term. We end up with d, and we assume again that dm is constant over I, integral y dA. Okay. Now let's further. So F3 can be written in terms of the change in the bending moment, right? But F3 also can be written as the shear stress times an area. And this area is going to depend on the size of the rectangular cross-section. Okay, so let's put some dimensions on here. Let's say that's depth B and height H. So F3 is equal to F2 minus F1, which is this, but F3 is also equal to tau times B dx. Okay, so it's some shear field that we're trying to determine smeared over this area that gives us a resultant force F3. So if these are both F3, we can equate these two. Okay, so let's do that and see what pops out. All right, so we end up with tau B dx is equal to dm over I y dA. Okay, now let's go ahead and kind of move the b dx over to the right, leaving tau by itself, which is what we're after. So we end up with dm dx 1 over IB integral y dA. Now remember, this y here comes from these y's here. Okay, and these y's are measuring up into this block above where we're measuring the stresses. We're measuring the stresses at y1, but this y that ends up in this equation is up in the block above y1. This is a very important thing to understand. Very confusing to students where this y comes from. It's going to be what we call the first moment of area, I believe. First moment of area of this block, of this cross section. This cross section right here. Okay. Okay, so let me just say that again. This thing here is called a first moment of area. And notice where it comes from. It comes from, this guy right here, comes from this right here. This is the y. And this y comes from this right here, this my over I. And this my over I comes from measuring sigma 1 and sigma 2 at some distance y greater than y1. So it's up in here somewhere. Okay, and so this guy here is what's called the first moment of area of the cross section above where we're looking at the stresses. It's going to be with respect to that guy right there. Okay, let me so let's clean that up. So tau then is dm dx 1 over IB y dA. Now we know what's dm dx? Dm dx is v. So it's v over IB, the integral of y dA, and then we're going to denote this by q. Okay, so it'll be v q I b. Okay, now let's come back to signs. Okay, so what's the signs that we assign? Usually Usually what we do is we treat everything as a positive quantity and then make tau simply point in the same direction as v. Okay, so we treat everything as positive and simply make tau point in the same direction as v. That's the common convention with shear. Okay, so let's just solidify this idea of Q a little bit more. Let's say we have a beam. Okay, here's the cross section. Okay. Here's the neutral axis. And let's say here's our y1. So we want to measure the stress along this line here. So when we measure Q, we want the first moment of area of that cross-sectional area, right? This hatched region right here, okay, above where we're measuring the cut, or if y1 was negative, it would be below where we're measuring the stress. And then this would be B, and this would be H. So if you want to determine Q, let's just determine Q of this shaded region. So Q is y dA, but we know that this is just a square, so we end up with an integral from y1 to, let's call it h over 2, y times b, right, because this is just a constant term, the depth is just constant, dy, and then that comes out to being b over 2 h squared over 4 minus y1 squared. Okay, so if you're given y1, where you want to know the stress, this right here is the analytical expression for Q for a rectangular cross-section above y1. So we can take this guy right here and now plug it in here and simplify tau into a kind of a more specific equation for this particular cross-section, which is what we want. Okay, so tau then, if we do that, it ends up being v over 2I h squared over 4 minus y1 squared. Okay, this is great because now we can see how tau is a function of y1. Just like before, we had that sigma was minus m y1 over I. These are the same y's. Okay, this is y1 over here where we measured sigma. This is the same. We're just using a different notation because we had a whole bunch of y's running around. And this is the same I. Okay, this is from the bending moment diagram, and this is from the shear moment diagram. Notice if you plotted sigma, right, it would look something like this. Okay, so if we plot sigma, it looks something like this, right, as a function of, this was y, right? And here, if we plot it as a function of y, notice that when y is 0, the shear stress actually has its maximum value. Okay, when y is 0, the normal stress is 0 at y1 equals 0, but the shear stress is maximum at, this will be called tau max. And then when y1 is equal to h over 2, plus or minus, right, this whole thing is 0. And then it's a quadratic function in between. So it looks something like this. Okay? So this is tau, and this is sigma. Okay, very important you understand the different notions. So you go to one location, y1. You grab the bending moment at a some position x. You go to the same y1 for v and grab v for the same x, same i's, and you can get both the normal and shear stresses acting at that location. Okay, and then this is important for you to know the functional representation and how tau changes as a function of y1. It's a quadratic function, it's not a linear. So it's probably the first time we've seen something like that. Okay, so let's do a simple example to kind of bring this into focus a little bit. All right, so let's have a simply supported beam again. It's our favorite beam. And just a distributed load, so it's very simple. Q is equal to 160 pounds per inch. This is A, B. The length L is 3 feet. And we want to measure now the stress 8 inches from the right endpoint and 1 inch down. 1 inch down. So we want to actually, so now they've given us a location where they actually want the stresses right along this point here. It's a rectangular cross section. Okay, so we end up with H equals 4 inches. B equals 1 inch. Okay, so the first thing you do is statics. Okay, because we want V of x and m of x at the point specified. Okay, and so you'll go through the process of computing reactions, computing the shear and bending moment diagram, or you can even just cut the beam right at the location and measure the shear and the shear force and the bending moment at that location without plotting the entire diagram. Okay. In this case, the shear diagram just it's not very good, but anyway, you know what it should look like by memory at this point. These particular simple cases. And so we actually want the value right here, right? 8 inches. 8 inches. Okay, so the V of x that we want, let's call this point C. So V at C is minus 1,600 pounds, and M at C is 17,920 inches. And again, this is another opportunity for you to do some statics if you're struggling with these kinds of problems. Make sure that you can do all the statics and come up with the diagrams and the values that I did. The moment of inertia of a rectangular cross section is just BH cubed over 12, and right, so there's B and H, Z, Y. Okay, and so in this case it's 5.333 inches to the fourth. Okay, and so now we're just about done. If we want sigma at point C, it's just minus my over I, where now y is what? If this is 4 inches and we want to measure 1 inch down from the top, it should be 1 inch up from the neutral axis. That's how I read that, at least. And then it's, so you plug in the numbers, you get minus 3360 psi. Tau C is V at C, Q, C, I, B. Okay, except now we have to figure out QC. Remember, QC now is going to be the first moment of area of this cross section above where we're measuring Y. And that's simply, you can compute QC as the area above point C times the distance y to the centroid of this area here. Okay. So that's equal to, so we end up with, plug everything in, we get 450 psi. Okay. So you can see, I mean, shear is there, but it's pretty small. And so it's an order of magnitude difference between the shear and the bending. And so one of the reasons we use kind of these blended theories that aren't exactly right, but they're definitely good for the kinds of problems we're looking at.